Hey everyone. So I know that we already went over this PowerPoint and presentation before we were off of school for the past 2 weeks, but I wanted to take some time and go back through it and just kind of highlight some of the major points since we were midway through this unit. And I think it's really important that we go back and just refresh a little bit so then we can get a better understanding of each of the laws moving forward and eventually apply this to the quantitative portion, which will be starting next week. So what I need for you to do is to go to your backpacks and grab out the note sheet that goes along with this PowerPoint. This way you can follow along. And like I said, I'm just going to kind of highlight some things, some of the most important stuff for you. And then tomorrow, what you're going to do is you will answer questions based off of your note sheet. All right. So first thing, what is a gas? Well, a gas is a state of matter and it has very high energy. And we know that because when we look at gas behaviors, we can see that they move around like crazy and they never stop. And they bounce off of the containers of the wall or the walls of the container which they're stored in. So that's what you're seeing here. They're just kind of bouncing off of the containers and then continuing on without losing any energy at all. And gases also have a low density, meaning that they want to spread apart from each other. Gas molecules, they want to fill the container up in its entirety. So they spread apart. This way they can equally distribute through the container or throughout the container. And when gases have a high density, that means that they're pressurized or they're condensed. And that's when they can be very, very dangerous. So gases can be monoatomic, diatomic, or polyatomic. Monoatomic gases consist of just one atom. So helium, which is not, it doesn't have the He here, but helium would be right here on the periodic table, that can exist all by itself. It can just be one single atom floating around, happy as can be. Diatomic gases are made up of two atoms, and so there are certain types of gases like hydrogen, and then here chlorine, that they must be attached to another one of themselves. So that's what that little 2 is right here. This 2 means there are two chlorines bonded to each other. And then lastly, polyatomic gases are made up of more than two atoms. So things like carbon dioxide, right? You have one carbon, and then this little 2 subscript indicates that there's 2 oxygens as well. So there's 3 atoms altogether. And then in this one, nitrogen dioxide, this chemical formula indicates that there's 1 nitrogen, and then this 2 tells me there's 2 oxygen atoms. So you have 3 atoms altogether. Okay. So here's some unique properties of gases. Gases have mass, and it's easy to compress a gas. You've probably seen compressed gases at least once in your life. If you've ever been driving and you see a big tanker truck, inside of that tank are compressed gases. Or if you've ever gone to a party store and picked up balloons, the tank that holds the gas that fills the balloon is a helium tank, and all the helium in there is compressed. Gases want to fill their containers completely. So I've talked about this before, where if I take air freshener and I spray it in the front of the class, eventually the particles will distribute and they will move to the back of the class, and the whole classroom will smell just like that air freshener. Gases will diffuse or move through each other, so they will pass through each other. So if I am spraying one type of gas or one type of air freshener on one side of the room and another on the other side of the room, those 2 molecules will pass through each other and you'll be able to smell both no matter where you are in the room. Gases can exert pressure on their surroundings, okay? And that pressure comes from them bouncing off of the walls of their container. And our bodies heavily rely on that pressure. We actually need that pressure. If it weren't for that pressure that gases exert on our bodies, then we would be a puddle on the floor, or our lungs wouldn't even be able to function. Okay, best case scenario. So the pressure of a gas depends on its overall temperature. So this slide basically says that gases, they never stop moving. The molecules are in constant motion and they move in straight lines. And when they bounce off of something, they start moving away in the opposite direction in a straight line. Gases aren't attracted to each other and they're not repelled. So gases don't want to get closer to other gas molecules, and they don't even want to stay away from other gas molecules. They just kind of do what they do. And as I said before, gases move in a straight line. So when they hit the wall of their container, they just change their direction and move in another straight line. And this just keeps happening in these straight line motions. When gases collide with their container walls, the type of collision is called an elastic collision. And so what that means is that energy is not gained and energy is not lost. Right? So this picture right here of this golf ball smooshing in together, that is a non-elastic collision. That means that energy is lost. Okay. By it condensing here, we can see that some of this energy is lost in that condensing motion. All right, so gas molecules are elastic. They're actually perfectly elastic, where they move in a straight line, and when they hit something, they move in the opposite straight line and do not lose or gain any energy at all. All right, so this slide here is demonstrating what I said about the collisions being elastic. Okay, these are examples of non-elastic collisions, right? You can see in both cases that the ball in each situation, it is being compressed and therefore it's losing energy. All right, kinetic energy and gas. So kinetic energy is the energy that a gas molecule has while it's in motion. And unless gas molecules have reached a temperature of absolute zero in which they have no energy, then they are in constant motion. So the energy of a gas is directly related to its temperature. So if the temperature is really high, meaning that it's really a really hot temperature, then the gas molecules will be very high energy. And so you can actually increase the amount of energy gas molecules have just by upping the temperature. And I've talked about this before in class. I said how when we go to the gym for pep rallies, the more people that are in the gym increases the temperature of the gym overall, right? All that body heat pumping into the gymnasium then causes the gym temperature to go up, and therefore the molecules of gas in the gym are moving much quicker. And then oppositely, the low temperatures cause gas molecules to have low kinetic energy. So you would actually see when you turn temperatures down or when the temperature gets lower, the gas molecules will move much slower. And we can see this when we practice using the PhET simulators. Okay, most of a gas's volume is empty space, and that's because gas particles are extremely small and they spread out to fill up their entire container. So the molecule, the gas molecule itself, is incredibly tiny, like teeny, 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 tiny. However, they want to fill up the whole entire container. So we say that the volume of a gas comes from the container that it's being stored within. So the volume of a gas in an empty 2-liter bottle of soda is 2 liters of gas. Okay, so there are 4 different variables that we use to measure gases, but we're only going to worry about 3. So volume is represented by V, temperature is represented by T, and pressure is represented by P. Number of moles is represented by N, but we're not going to worry about the number of moles in here. We're just going to focus on these 3. Okay, and then when we eventually get to solving gas law equations, these are the three variables that we'll be using and focusing on. So temperature is a measure of heat, and the amount of kinetic energy tells you how much energy of motion, or equals the energy of motion. And when there's more motion, there's more kinetic energy, and that is higher temperatures. And then when there's less motion, that means that there's a lower amount of kinetic energy, and the temperature of the gas is much lower. Now, when we do gas law problems and when we talk about gases, we're going to use the Kelvin scale. And the reason being, it's an absolute scale. So what that means is the Kelvin scale bases temperature on an absolute scale where temperature corresponds to the amount of motion of the particles. So basically what you can take away from that is that at absolute 0 or 0 kelvins, all gas molecules can no longer move. They just stop moving completely. There's no vibration, there's nothing. And then this is the whole scale altogether. It goes much higher than this. So during this unit, when we are calculating the gas law equations and solving for variables, we're always going to want our temperature to be in kelvins, and this right here shows you how to do that. So if I want to go from Celsius to Kelvin, then what I do is I add 273 to my Celsius temperature to get kelvins. So anytime you go from Celsius to Kelvin, you add 273. Okay, we measure volume in liters. Now, pressure, gas pressure comes from the molecules of gas hitting the walls of their container. And so the more collisions there are with the walls of the container, the more pressure that exists within the gas. All right, so because the area is much smaller here, there's going to be way more collisions, and therefore the pressure is going to be higher. If I tell you guys to run around in a classroom versus running around in the gym, there's going to be way more collisions between students in the classroom running around than there are the gym, because the size of the classroom is much smaller than the gym. So here are the units of pressure. These are the ones that are like the typical ones that you'll see. However, we are just going to concentrate on atmospheres in here. So when you watch the weather and the meteorologist talks about the barometer, they're referring to pressure in terms of millimeters of mercury, or mmHg. And we are going to use atmospheres. Okay, so for all gas laws problems, everything will have to be in atmospheres. And your body is acclimated to having 1 atm of pressure, or 1 atmosphere of pressure on you at all times. When the atmospheric pressure changes, your body notices it. So when we have weather changes, your body might pick up on it. Right? You might have achy joints. Or when you take off or land in an airplane, you can feel that pressure change in your ears. We use manometers to measure the pressure of a gas. And we're not going to worry about this. All right, so here are the laws. Boyle's law relates pressure and volume. And so what Boyle's law tells us is that when the volume is decreased, the pressure increases. All right, so they are an inverse relationship. When volume is high, pressure is low. When volume is low, pressure is high. All right, Charles' law. Charles' law relates volume and temperature. So that means that pressure is held constant. So Charles' law is V1, or initial volume, over T1, initial temperature, is equal to V2 over T2. Right? And what that tells us is that they are directly proportional. When the temperature goes up, the volume goes up. And this is how we fly hot air balloons. The reason that hot air balloons work is because of Charles' law. When you heat up the temperature of the gas inside the balloon, the volume of the balloon goes up, and therefore the balloon can go